Ladies and gentlemen, good morning. Welcome to the joint academic conference by the Future Science Prize and the University of Hong Kong. My name is Lansai Richard, major in mathematics at the University of Hong Kong. First of all, I would like to invite Professor Max Shen, Vice President and Pro-Vice Chancellor, Research, the University of Hong Kong, to give his opening remarks. Professor Shen, please.
Thank you. Good morning, dear friends and colleagues, ladies and gentlemen. When I walked into this room, when I saw the poster, I know this is an award for mathematicians. Look at the formulas. And I'm really happy to see many young people here too to celebrate this award. So this is in fact already the second time in my career here in Hong Kong U to celebrate this award. Last year, we also have two colleagues from Hong Kong U won this award. But this time, it's for mathematicians. I think this is really, like one of the people mentioned in the speech, is that this is a fun, but a really far-reaching award. So I'm really happy here to honor Professor Ngaiming MOK, everybody know him already, to receive this award. But this is also a joint conference, and then there will be academic activities after the award ceremony. So Professor MOK has been awarded the 2022 Future Science Prize in Mathematics and Computer Science in recognition of his exceptional contributions to a few areas in mathematics and computer science. And then, I try to actually go to his website to study all these areas, but I don't fully understand. So I asked him, what does it mean by several complex variables? He did a very nice explanation. And then he also does research in complex differential geometry and algebraic geometry. So he's well known in the mathematical community for his global perspective of pure mathematics. And then I have actually talked to many of my friends in mathematics, everybody was really very high on his accomplishment. And he was able to solve many conjectures and a lot of hard problems by combining a lot of technical tools from different areas in mathematics. And then this is why he was awarded this 2022 Future Prize Award. And this award was only established in 2016. In just a few years, it has become one of the most important awards, not only in the region, but also globally. So I hope this trend will continue. That we'll have more Hong Kong U researchers to get into this award. So in Hong Kong U, as I mentioned earlier, this is the second time in 2 years we are celebrating our faculty members for getting this important award. So this prize is not only a recognition of Professor MOK's scholarly achievement in basic research, but also is a testament to the university's dedication to research excellence of the highest order. So we hope this is not only recognition for the older generation, but I see a lot of young faces here. I hope the young mathematicians, the young researchers in Hong Kong U will carry the torch and won similar awards in the future. So again, congratulations to Professor MOK, and thank you for your work and dedication to Hong Kong U. I also have to make an announcement. There will be a roundtable discussion on cross-fertilization in mathematical research following Professor MOK's keynote speech, and we invited speech by 3 distinguished international scholars. So I hope all of you will enjoy this joint conference today. Thank you very much.
Now may I invite Professor Shouwu Zhang, Subcommittee Chair of Mathematics and Computer Science Prize of the Future Science Prize, for his welcome remarks.
Ladies and gentlemen, on behalf of the Future Science Prize, I'm very pleased to welcome you to this joint academic conference. Today, we are here to celebrate the work of Professor Ngaiming MOK from Hong Kong University, who was awarded the 2022 Future Science Prize in Mathematics and Computer Science for developing the theory of varieties of minimal rational tangents in algebraic geometry to solve several long-standing problems and proving X-Chanuel's conjecture for Shimura varieties. As we just heard that this is the second cooperation between the Future Science Prize and the University of Hong Kong to hold the academic report. Last year, Professor Kuan Yun and Professor Malik Paris won the 2021 Future Science Prize, the Life Science Prize. Their dedication and scientific rigor reminds us the human ingenuity and the key to the world's most pressing challenges. And after Professor MOK received the prize, I actually was asked by the vice president and by Hong Kong University there, what about the next year? Maybe somebody should award the material science prize. Okay, so complex differential geometry, a core field in modern mathematics, plays an important role in theoretical physics and in many branches of mathematics. Professor Ngaiming MOK made two fundamental contributions in this field and in other related areas. The first contribution is the theory of varieties of minimal rational tangents in algebraic geometry that he developed with Junmark Huang. The basic notion of the VMRT was derived from MOK's early work in differential geometry and has been used to prove the Kähler rigidity of irreducible compact Hermitian symmetric spaces, as well as the conjecture of Lazar's fields concerning holomorphic maps from a rational homogeneous space to projective manifolds. The second contribution is his proof against Chanuel's conjecture for Shimura varieties jointly with Jonathan Pila and Jacob Zimmermann. The original Chanuel's conjecture is a major conjecture in number theory. The X-Chanuel's conjecture on any Shimura variety is an important analog of Chanuel's conjecture in hyperbolic geometry. The theorem MOK and his collaborator proved has become important too in arithmetic geometry. Before I continue, I just say a few words away from this report, this note. And in fact, I visited Hong Kong University right after MOK returned to Hong Kong, and he had a first conference, I remember in the beginning of the 90s. And that's the first time I visited Hong Kong. There I met many colleagues and friends, and they're like a professor, I'm a letter Professor Alan Beck, and a Professor Wustos, and my advisor Wang Yuan, and many people there. So I'm really glad that this prize eventually returned to Hong Kong. Also, I took this opportunity to say a few words of my interaction with many guests of this conference. First of all is Professor Yin Tom Siu. I met him in 1984 in the summer school in Beijing University. So he is the first person I met among this group. Then is Professor MOK and my friend Wei-Ping Li. We met at Columbia University, where Wei-Ping and I are a graduate student. Professor MOK just started with an assistant professor there. In fact, Professor MOK didn't know that. Actually, I know his name much earlier than this time. When I was in Chinese Academy of Science, Professor Lu Qiken already reminded me of Professor Mark. He told me that Mark once returned to China right after he finished his postdoc. I was really touched. Then I also met Professor Wustos at Princeton when I was a visiting graduate student. So, so the guests of this conference, most of them is my friends, the classmates, a lot of people. So I'm glad to, I'm really regret that I could not go there because of the pandemic. Okay, before I hand the floor to our proud laureate, I would like to introduce you the Future Science Prize, which is a privately funded science award initiated by a group of scientists, entrepreneurs. The Future Science Prize aims to celebrate the accomplishments of scientists who have made extraordinary scientific contributions, mainly in mainland China, Hong Kong, Macau, and Taiwan. There's no restriction on nationalities or laureates. There are three major categories at present, namely the Life Science Prize, the Physical Science Prize, and the Mathematics and the Computer Science Prize. With each award of $1 million respectively. The Future Science Prize has been awarded the 27 laureates since 2016. All laureates are highly accomplished, widely recognized scientists whose research has made extraordinary impacts in life science, physical science, chemistry, mathematics, and computer science. Congratulations, Professor Mark. Thank you for your extraordinary contributions to modern mathematics. Lastly, I wish today's Future Science Laureate lecture a big success. Thank you.
Thank you, Professor Zhang. Now may I invite the moderator, Professor Ngaiming, Professor, Department of Mathematics, Faculty of Science, the University of Hong Kong, to the stage. Professor please.
It's my great honor to introduce our keynote speaker, Professor Ngaiming MOK, the Edmund Peggy Zhang, Professor in Mathematics and Chair of Mathematics, HKU. Professor MOK was a graduate of St. Paul's Co-Educational College in 1975. He obtained his PhD at Stanford University in 1980, 5 years after his graduation from high school. He taught at Princeton University, Columbia University, and University of Paris before taking up a chair professorship in the Department of Mathematics at HKU in 1994. Professor MOK is recognized worldwide for his research achievement in complex geometry and several complex variables. He has received many prestigious awards. For example, the State Natural Science Award, Class 2 in 2007, the Berman Prize of the American Mathematical Society in 2009, and also recently, the Chan Prize of the ICCM 2022. Professor MOK also served on the editorial board of Inventions Mathematicae from 2002 to 2014. He also served as a member of the Fields Medal Committee for the International Congress of Mathematicians, ICM, in 2010. He was elected a member of the Chinese Academy of Sciences in 2015, and later a member of the Hong Kong Academy of Sciences in 2017. So the title of Professor MOK's talk this morning is Journey to the World of Numbers Through Complex Geometry. May I invite Professor MOK to the stage?
It's my great honor to be speaking here, sharing my passion for mathematics. I'd like to thank Future Science Prize for giving me this opportunity to share with you. The title of the talk is the charm of mathematics from geometry to number theory. So I was actually charmed into mathematics by many different things, certainly geometry and number theory. And I was trained first as a complex analyst and then as a differential geometer. But now I've been finding applications of complex differential geometry to many different areas of mathematics. Okay. So to start with, let's talk about elliptic curves. So these are the donuts. They are all diffeomorphic to each other, but they have different complex structure. And to define an elliptic curve that is a donut, so a compact Riemann surface of genus 1, what one does is to take a lattice on the complex plane, R2. All lattices are the same if you think about this as R2, but if you think of this as a complex plane, then there are different choices. And it's generated by 1 and tau. Tau is a point on the upper half plane. Now, different tau, so tau and tau prime, might give you isomorphic tori if and only if tau prime is obtained from tau by a certain substitution. This is a substitution by a matrix of the matrix in SL2Z. So that is A, B, C, D are integers. So everybody deals with integers. There's a function called the J function. This classifies all elliptic curves. So the J function is explicitly given. It's given by some formula, and these are invariants that can be computed based on infinite sums over the lattice. So the J function establishes an isomorphism with the complex plane. Okay, now as a complex differential geometer, I was trying to apply to some problem that could be related to number theory. There is the so-called universal or the elliptic curve. So how does this look like? So, okay, so here I was writing X gamma is a quotient of the upper half plane. E gamma is a family of these elliptic curves. All of them make up what is called the elliptic modular surface. An important invariant is the number of sections of this over X gamma. And they form then points of the commutative group of rational points over a function field. So this is the famous Mordell-Weil group. To treat this Mordell-Weil group, interpreting them as sections, so we were looking at, I was looking at what is now called the verticality of a section. So there are invariant metrics on this family. So this is two-dimensional. A family H cross C is two-dimensional. And then it is foliated by what are called horizontal sections. Horizontal sections are real linear combinations of the lattice points, varying with the base. So then there is the vertical and the horizontal, and then you can introduce a metric. This metric was in fact introduced by Satake implicitly, and using them to embed the Cougar families into projective spaces. And then when you take this vertical part, which I call eta, the verticality, then one can do differential geometry on them. And this is what I get. Okay, so the Mordell-Weil group of the elliptic curve is always finite. So there are only a finite number of sections. And the proof is by differential geometry. F is a lifting of a section. This is called an elliptic logarithm. It turns out that if you take second derivative, actually this is a modular form. Then I realized that if you use invariant metrics, then you can talk about this nabla, this inverted triangle, is the covariant differentiation. This is also a tensor living in the same space as the second derivative. And then I realized that they are the same by computation. So they are actually the same. That they are the same means that d bar of this object is equal to 0. Now, and then you can do commutation to get this differential equation. This is an elliptic equation with a negative eigenvalue. So if you have any section, you will have to satisfy this equation positive on one side and negative on the other side. And this is impossible unless both are 0. So this is just comparing two squares, but with the opposite sign. Now, this is very important. This equation is very important, this elliptic equation. Now, 30 years later, it turns out that this study is actually becoming more and more interesting to number theories. These are the so-called Betti coordinates and the Betti map. The Betti map has been introduced to study torsion points, among other things. And this is just the real analytic trivialization. You regard all the lattices as being the same over R2. And then Kovarja and others introduced a notion of the Betti multiplicity. Of course, for the modular case, you don't have sections except a finite number of them, the torsion sections. But in general, you may have sections by, you have other elliptic surfaces. And then when you take such a section, you can ask this eta. Actually, they introduce also this eta, which is the same as what we call the verticality, and then they introduce a multiplicity. This multiplicity MB minus 1 is the same as the multiplicity of eta, and also at infinity. And then Kovarja and others prove the finiteness of the number of points where the multiplicity is at least 2. And then Ulma Usua prove an effective estimate. So sometimes you prove qualitative results, and then you try to get effective estimates. As we were not aware of this, and then we gave another proof, but this is by differential geometry. The point is, however, that this is a completely different proof, and this proof can be generalized to higher dimensions. The point is that we make use of equations, actually in this case, a first-order differential equation satisfied by eta. This is a real differential equation, and certainly has something to do with the Gauss-Manin connection, but written in this form, in the context of differential geometry, turns out to be very useful. In fact, after my 91 paper, this should be 93, I had joint work with my student, my former PhD student, Wing Kang To, and we proved actually that for all Cougar families without constant parts, the Mordell-Weil group is equal to 0. So this is based on some generalization of the case of elliptic surfaces by looking at elliptic differential equations. And then we also get estimates for the rank of the Mordell-Weil group. In case of the base is a surface, what we get is that it's bounded by n being the fiber dimension multiplied by the degree of ramification divisor. What we were regarding, the modular, the abelian schemes as obtained by pullback of a classifying map. So our approach gives importance to the classifying map. So everything should be in terms of the classifying map. This estimate is just a geometric estimate. This has something to do with Hodge theory, actually. But actually, to get the Mordell-Weil group, one would have to study number theory. And this then leads to very difficult, very interesting arithmetic questions, which nobody has yet made any progress on. Then in high dimensions, there are the Ziegel upper half plane. The Ziegel upper half plane is used to parameterize higher dimensional analogs of elliptic curves. These are the so-called abelian varieties. The abelian varieties are CG modulo a lattice plus condition that they can be embedded into projective space. So, and then there was Riemann. So Riemann is really somebody who has done so much contribution to mathematics. The Riemann bilinear relation is the saying that, well, the lattice can be generated by the standard basis together with a symmetric matrix, tau, such that the imaginary part of tau is positive. And then this is the domain. This is the domain. This is the Ziegel upper half plane. The Ziegel upper half plane is actually biholomorphic to something which is bounded. These are the bounded symmetric domains, very much studied by the late Professor Paulo Geng. In fact, the bounded symmetric domain forms the basis for his the Natural Science Award, Class 1. Okay, so then in analogy to the SL2Z, then you have the SPGZ. And then this gives you the moduli scheme for the abelian varieties called AG. So this is a very important space studied by number theorists and algebraic geometers. Well, the balanced numeric domains as examples include the complex ball, and then 4 series of classical balanced numeric domain, irreducible ones, and 2 exceptional cases pertaining to the exceptional Lie group E6 and E7. Then is my second attempt to move into something relevant in number theory. And so my article actually SPEC's article introducing the model field group from a complex differential geometry point of view was largely unknown to the number theorists community. So, but however, it was read by my colleagues at Orsay in University of Paris when I was working there from 89 to, I was working there from 89 to 94. So after I have left for Hong Kong, they invited me back to discuss. And then they were working on something about Hacker correspondences. So there's certainly number theory, but they have a question in dynamics who's trying to find a commutator of the what's called the Hacker correspondences. Hacker correspondences are the subvarieties or product of balanced numeric domains, so to speak. With certain, of course, they're modular in the sense that they're totally geodesic. Okay, and so Clausel Ulmer were my colleagues in Paris who invited me, and then they reduced their question to a question about measure-preserving maps. So as a complex analyst and differential geometer, this is certainly the type of question I could deal with. So then back in 2012, I proved with my former PhD student, Sui Chung a solution to their problem, and this appeared in the Crowd Journal. And the elements of the proof, so as a corollary of this, of course, this original purpose of proving this was that they could characterize the commutants of the Hacker correspondences as being also modular. So I just want to say a few words about how the elements of proof. It turns out that the elements of proof comes from complex analysis and also the differential geometry. So the first thing is just a question about extending analytic maps. And this is a result due to Webster and Huang. And the other element is that in the case of rank 1 high dimensions, I make use of a very classical result of Alexander in 1972. This is the statement that if you have a local biomorphism at the boundary preserving a sphere, part of the sphere, then this must come from a global automorphism. And then with we prove an analog of that for the higher rank symmetric spaces. This ties up with the differential, with the geometric structures, actually with the theory of VMRT. Yeah. Okay. Now, so of course, then dealing with Hacker correspondences certainly is a component of number theory, but I was interested to get actually in touch with real numbers. I mean real, I don't mean real in the sense of a field, but actually number theory, numbers and not just function fields. So then I was very interested to find out that there is the Laureate conjecture. As a matter of fact, Professor Witthos was visiting Hong Kong U in 2012 and giving a series of lectures on the Laureate conjectures, and during which time I was introduced to this subject. And then it was Zanier, and then later Pilar Zanier, who proposed a certain scheme for solving questions concerning distinguished points or special points, including torsion points and special points in the sense of Shimura variety. A special point for the upper half plane is a point such that the both tau and j tau take on the algebraic values. And then the extension field must then be equal to 2 by work of Schneider in transcendental number theory. And then for Shimura variety, you can generalize this notion. And it was Sanier who realized that in order to solve the Andreatte conjecture, what one has to do is to decompose it into 2 components. One component being algebraic number theory, having to do with Galois orbits. The other component being completely differential geometry, having to do with the theoretic closures of images of algebraic sets under the projection map, which is the uniformization map. So in the case of upper half plane, this is a J function. Then you have the analog for the other spaces. I was in, well, okay, so let me explain the background in transcendental number theory. So there was a Lindemann theorem, the classical theorem in 1882, in which the statement is given here. If you have n numbers which are Q-linear independent and they are algebraic, then when you take the exponential, then the exponential, these n exponentials are algebraically independent. So the transcendence degree of the field generated is equal to n. The Chanuel conjecture, Chanuel was a student of Serge Lang's at Yale. So the statement is that if you take complex numbers instead of algebraic numbers, then of course these numbers might themselves already be algebraic independent, or may not. But then if you join also the exponentials, the Chanuel conjecture is that the transcendence degree must be at least equal to n, 1/2. Now, if you could solve this, even in some special cases, you would get the algebraic independence between E and pi. This is widely open. So Lindemann theorem is a special case when the first n were algebraic dependent, and therefore it says that the others are algebraically independent. So Baker's theorem is sort of a special case when assuming that the exponentials are algebraically dependent, right? But then this is a special case. One gets linear independence over Q bar of certain the logarithms together with 1. Now then there comes something that is related to the Andreatte conjecture. As I said, there is the second component, which is the geometric component dealing namely with the Sarsi closure. I will explain why that is an analog. So it was Klingler, Ulmo, Yafayev who proved in 2016 this theorem, this solution to the Ax-Lindemann conjecture. They proved that the Sarsi closure would be the whole space unless it's contained in some totally geodesic subspace. In their language, they call these weakly specials of variety. So in analogy to the special points. These were defined in group theoretic terms, but in differential geometry, they correspond exactly to total geodesic subsets. I was in fact led to this type of questions from a completely different path, but let me explain later. So the key argument, 2 key arguments are the counting theorems of Piller-Wilke. This has to do with mathematical logic, the O minimality theory, and the other element is complex differential geometry, familiar names to you, Huang and Tou. So Huang is my collaborator in algebraic geometry, and Tou my former PhD student. Now recently, Zimmermann and Piller and Shankar have posted a solution of the full Andreatte conjecture. The case of AG was settled by Zimmermann already published. So about the mathematical logic part, this has to do with counting of definable sets. So definable sets are defined by certain theory, and the theory is explained here. So this is in model theory, so you wouldn't think that mathematical logic has something to do with number theory, but actually it does in a serious way. So there's a notion of O minimality. So it's defining certain subsets of real space Rn, and subject to certain axioms. And it was found that a certain theory, which has to do with the construction of the fundamental domains, like the Ziegel set and so on, actually belongs to this theory. This theory has a special feature that the S1, one-dimensional definable sets are unions of intervals and points. And also S0 would be finite point sets. So the counting theorem of Piller-Wilke, which was also motivated by work of Bombieri-Piller in the Diophantine estimates, actually says that in a definable set, in this theory, the points of bounded height less than or equal to t grows sub-polynomially. It cannot grow polynomially, for instance. And the Z algebraic means those points that lie on algebraic curves or algebraic sets of high dimensions. So it says that if you have too many points, it means that there must be some algebraic curves. So that's the upshot. So often these algebraic curves would have some relation to groups, and then you would be able to generate some one-parameter subgroups and so on. So this is the basis of the relation. Now, on the complex analytic side, the contribution from Huang To, this actually can be derived from the Lelong monotonicity formula. It says that if you want to estimate volumes on the Euclidean space, according to Lelong, you can get a monotonicity, and this is also related to the projectivized volume when you project the projective space. But the same formula with exactly the same proof can be applied to the ball or to bounded symmetric domain, with the consequence that actually the volume of the intersection, this means I actually take the intersection of Bx0R with V. Then the volume is bigger than or equal to C, some exponential in the radius. So this is used in an important way in the arguments by Klingler, Yafeev, and Ulmo. Now, I was led to Ax-Lindemann by a completely different path, trying to solve a problem in the differential geometry. And then I realized that my method could be used to tackle the what is called the Ax-Lindemann conjecture. I didn't know even this name. So I was very delighted to find that this is of interest to the number theorists. Of course, they were interested in gamma being arithmetic, because these are what are related to number theory. So I only wrote at that point a paper in the rank 1 case where the gamma need not be arithmetic. I have at this point techniques that should lead to me finally to a solution of the Ax-Lindemann in the non-arithmetic case, but up to this point only a very the case of what I call bioalgebraicity in the compact case has been published, and this was publication with Chen, a former PhD student of mine at Hong Kong U. So well, I guess the point I want to drive is that this was for me a differential geometric problem, and I introduced the importance of two objects which finally become important in the solution of the Ax-Chanuel conjecture with the Piller and Zimmermann. The first thing is that I introduced the child scheme by making use when you have well, this of course is just Ax-Lindemann, a special case of Ax-Chanuel. But then one looks not just at one algebraic variety, but you look at a whole family of them, or the modular family of them, and then you should introduce metric. To introduce metric, the important thing is that maybe I would jump over this, but the important thing is simply to say that in order to deal with this foliation, I have to prove that foliations are algebraic. In order to prove foliations are algebraic, then I make use of results of mine with Zhong Jiaqing, the late Professor Zhong Jiaqing. This was an article in 1989 in the Annals, dealing with L2 estimates of D bar, but working with the classes that are wider. These are the families of so-called Nirvanina class. And then finally, in the proof, actually, one makes use of differential geometry by looking at asymptotics of the curvature. Okay, so new elements were introduced into the subject. Okay, so about the Arc-Chanuel conjecture, let's look at some Arc-Chanuel theorem. This goes back to the X, which it looks like if you look at the Chanuel conjecture, you replace the numbers by functions, and this are the exponentials. It looks like this, but there's an extra term coming from the dimension. So they took formal power series, but you can think about just varieties. So there's an extra contribution from the varieties. On the other hand, you don't always have this. You have this under some assumptions, and the assumptions are equivalent to saying that these are actually you don't have the total geodesic subsets with respect to some metric, some Euclidean metric. Actually. Okay, so let me skip this. So the Arc-Chanuel conjecture for the J function was first proved in 2016 by Piller and Zimmermann. And actually, they also obtained the result with the J prime and J double prime with the derivatives. So this is about transcendence degree. But then the important thing that led me to believe that one should use at least intuition from complex differential geometry and algebraic geometry is the formulation of the Arc-Chanuel conjecture in terms of unlikely intersection. So in terms of unlikely intersection, it says the following. If you look at this omega is the boundary symmetric domain, X gamma is the quotient, the product is then, this has an algebraic structure. Think about omega as lying inside CX.
You can share screen now. Thank you.
So take D to the graph of the uniformization map. So the uniformization map is highly transcendental. So this D is a highly transcendental complex analytic subset. Now you take something algebraic, W, the W here, this is algebraic in omega cross X gamma. You take the intersection, you have some expected dimension. And the statement says that if the dimension is bigger than expected dimension, perhaps you look at this, U is an irreducible component of the intersection. And if the dimension is bigger than what you expect, then the statement is that you project U to X gamma, then it must be contained in a weakly special subvariety that is a totally geodesic subset. Now, then there's the equivalent formulation in terms of the, in analogy with the original Chanuel conjecture or with the X-Chanuel theorem. It says that you can look at these functions. These are functions coordinates for the boundary symmetric domain. These are the so-called Harris-Chandra coordinates, the natural coordinates, the way that you write these domains normally. And then this phi j are the automorphic forms, so the modular functions. So you look at the function field generated by this, that is, you form the usual field operation with these functions, and you estimate their transcendence degree of this field. And then it says that it is going to be at least n, plus this is the dimension of the subvariety, a subvariety V that is not contained in the weakly special subvariety. So it says that you don't always have this inequality. You have to make the assumption that this does not lie in something special. Okay. Obviously, if you take an algebraic set that already belongs to a subdomain, the theorem is wrong. So you have to impose some condition. And what it says is that these are exactly the necessary, are the sufficient condition for the inequality to hold true. Okay. So then I want to say something about the meaning of this X-Chanuel conjecture on Shimura variety. Now, it has recently been brought to light that actually this has lots of implication to number theory, actually dealing with numbers, with rational points, and so on. The Zilberping conjecture is something on mixed Shimura variety that goes beyond the Andreot. You are looking at the abelian, modular abelian schemes and subvarieties thereof. Okay. So instead of taking omega mod gamma, you take something like this Hg cross X gamma, Hg cross Cg, and modulo some semi-direct product of giving you the modular family. Okay. And then it was also applied to the study of the Betti map. The Betti map, as I said, is related to what we call eta. Eta is in fact the differential of the Betti map. The Betti map simply says that you identify an abelian variety as a CG modulo the square lattice, the standard lattice, real analytically. Then you get a map into this torus. And then you have the level sets. The level sets are precisely horizontal sections. So this is the Betti map. But then you can study the Betti map restricted to a subvariety. Okay. So this is now a very much investigated area. And it turns out that we have the following consequence. This is a very important consequence called the uniform Model conjecture. It's now a theorem. So the Model conjecture was settled by Faltings. I think the article was 1983, actually. Proved the Model conjecture. This is very powerful intuition. So when you take a higher genus curve, so with at least 2 holes, so to speak, and you put them into a projective space, so the space should be curved. But the curvature of the space and the curvature of the ambient space are not are not related in some evident way. However, it was possible to do differential geometry in the context of so-called Arkelov geometry. And by Arkelov geometry, and also height estimates on single upper half-plane. So Hawkins was able to prove that if you take a number field, for instance, Q, you have this curve defined over Q, or a finite extension of Q. The number of k rational points is actually finite. Now, if you take a curve C and you embed it into the Jacobian, and then you can look at the k rational points on C, right? So assume, of course, that C is defined over some number field. And then it was proven by Dimitrov, Gao, and Habecker that the number of rational points can be effectively bounded. So in number theory, it's one thing to say that you have a finite set. The other is to be able to effectively bound it. Of course, finally, then also effectively bound the solution, the heights of the solution. If you can do all of these, then there will be eventually algorithms for you to actually find out all solutions to the equation. This is an important step, at least to say that you have a bound in terms of some invariant. And the invariant is bounded in terms of 3 objects. One is G, the genus of the curve. 2 is D, is the degree of the field K over Q. And the third one is the Mordell-Weil rank rho of the Jacobian of the curve C. And the proof of that actually makes use in very essential way Gauss' work on the degeneracy of the Betti map. And the degeneracy of the Betti map actually also relies on the Ax-Chanuel conjecture on mixed Shimura variety, which makes use in a very important way ideas of the proof, or the proof of the Ax-Chanuel theorem on Shimura variety that I had with Piller and Zimmermann. So let me stop here. Thank you for your patience.
Thank you, Professor Mo, for the very interesting talk. And so we are going to have a number of invited speakers to deliver their invited lecture. But before that, the Future Science Prize has made a short video to explain the work of Professor Mo. So we will play this video first, and then we will invite our speaker to deliver their lecture.
For things that don't exist, imaginary numbers are remarkable in the power and scope of their application. There is no number that can be multiplied by itself or squared to give -1. Pretending there is, however, gave birth to one of the biggest developments in mathematics. I, the name mathematicians have given to the square root of -1, can be used in arithmetic just like real numbers. Adding multiples of I, or imaginary numbers, to real numbers creates so-called complex numbers. And geometry performed with complex numbers lies at the intersection of many different mathematical fields.
In modern number theory, complex analysis is essential. Without complex numbers, there would be no fundamental theorem of algebra. So you can imagine that algebra would be very much hampered in its development without complex numbers. A lot of modern physics would not be imaginable without the introduction of complex numbers.
In the field of complex differential geometry, Ngaiming MOK, a professor of mathematics at the University of Hong Kong, solved an important problem called the generalized Frankel conjecture. To do so, he developed a powerful new mathematical tool called varieties of minimal rational tangents. Complex differential geometry involves the study of manifolds. Like making flat maps of the surface of the Earth, a manifold is an object that may be curved in any dimension, but can be covered by regions in a flat space, known to geometers as Euclidean space.
The generalized Frankel conjectures concerns the complex structure of a compact algebraic manifold under some assumption on its curvature, which is positive or semi-positive. So in order to solve this problem, I make use of the Ricci flow and algebraic geometry, reconstructing the complex structure of the underlying compact Kähler manifold from its supply of rational curves. From the minimal rational curves, I consider the variety of minimal rational tangents and reconstruct the manifold.
Another major achievement of Professor MOK's work relates to transcendental numbers. These are numbers that cannot be expressed as a solution to a polynomial equation or expression with multiple algebraic terms with integer coefficients. The most important example of a transcendental number is the constant pi.
Most real numbers are transcendental. But if you show me a number in its decimal expansion, it would be very difficult for me to tell whether it's transcendental. As a consequence, showing that pi is a transcendental number is a very difficult problem and makes use of very difficult mathematics, and was a major achievement.
Like pi, the constant e, or base for natural logarithms, is also transcendental. Can one be related algebraically with the other? Mathematicians think the answer is no. This idea can be simply put, but proving it remains an unsolved problem of number theory. Working together with mathematicians Jonathan Peeler and Jacob Zimmerman, MOK has, however, proved a related problem in functional transcendence theory called Ax-Chanuel's conjecture for Shimura varieties.
The Chanuel conjecture is a major conjecture in transcendental number theory. As a corollary of the conjecture, if confirmed, would say that pi and e are algebraically independent. The Ax-Chanuel conjecture for Shimura variety is a function field analog of the Chanuel conjecture. This is a major achievement, and as a matter of applications, major results in number theory concerning rational points have been proven using the theorem on Ax-Chanuel conjecture for Shimura variety that we have obtained.
Since solving the generalized Frankel conjecture, and after returning to Hong Kong, Professor MOK has worked with the Korean mathematician Jun-Muk Wang. Together with their students, the two professors have advanced the varieties of minimal rational tangents, the tool of algebraic geometry that Professor MOK created, and used it to solve a series of long-standing problems in algebraic geometry in an area of the field called uniruled projective manifolds. For developing the theory of varieties of minimal rational tangents in algebraic geometry to solve several long-standing problems and proving Ax-Chanuel's conjecture for Shimura varieties, the 2022 Future Science Prize in Mathematics and Computer Science goes to Professor Ngaiming MOK.
Okay, the first invited speaker of this conference is Professor Yam-Tong Siu, who is currently the William Edward Byerly Professor of Mathematics of Harvard University. Professor Siu received his MA degree in mathematics from the University of Hong Kong in 1963, then an MA degree from the University of Minnesota 1 year later, and a PhD from Princeton University in 1966. Professor Siu is a dominant figure in the field of several complex variables in mathematics. In 1993, he received the Stephen Bergman Prize for his contribution to this area. His research interests involved the interface of complex variables, differential geometry, and algebraic geometry. Professor Siu is a member of National Academy of Sciences, USA, a fellow of American Academy of Arts and Sciences, a foreign member of Chinese Academy of Sciences, a corresponding member of Göttingen Academy of Sciences, a member of Academia Sinica Taiwan, and also a member of Hong Kong Academy of Sciences. In addition, Professor Siu has the honor of delivering 3 invited addresses at the International Congress of Mathematicians. 2 of them were plenary addresses. The title of Professor Siu's talk is Global Non-Deformability of Irreducible Compact Hermitian Symmetric Manifolds. So may I invite Professor Siu to deliver his lecture.
So I'm displaying by share screen almost every single word I'm going to speak, because by Zoom, sometimes it's difficult to hear. So I have to make sure that everybody's following. I'm displaying almost every single word. And I'm very pleased to have the honor to help celebrate the award of the Future Science Prize to Professor Ngaiming MOK. So I'm going to talk about global non-deformability, which is different from rigidity. You just take a holomorphic family of holomorphic objects over the open unit disk. So with fibers x sub t, t is the parameter in the unit disk. And local non-deformability or rigidity simply means that the fibers near the center fiber would be biholomorphic to it. Yeah. So that means that there's no small deformation of the center fiber. On the other hand, global deformability of a holomorphic object, Y, means that if every fiber other than the center fiber is biholomorphic to this object Y, then the center fiber is also biholomorphic to Y. And that means there's no large deformation of Y. Kodara and Spencer in 1958 asked the question whether the complex projective space of dimension n, Pn, emits global large deformation different from Pn. That means every global deformation must be biholomorphic Pn. And this is related to the question of non-existence of complex structure of S6 as pointed out by Alfred Adler in the late 1960s. So Alfred Adler introduced a new version of continuity method, which not only proves the global non-deformability of Pn, but also the non-existence of complex structure for the sixth sphere. It was published in the American Journal in 1969. The local rigidity of Pn offers openness of biholomorphism of fiber to Pn. Okay. So if you have a fiber that's the same as Pn, or neighboring ones would be the same as Pn, so there's no openness. And his continuity method would give closeness, yielding global non-deformability. For S6, the deformation is from the standard one, defined by the Octonians, to an integrable, almost complex structure. So his continuity method is for a modified notion of Kähler structure. With closeness of the Kähler form, to be interpreted as modular torsion tensor of integrability of almost complex structure. So if you have integrability, then it's the same as the regular. So he uses this deformation to show that there's no integrable one. So if there's one, then you can deform the standard Ortonian one to the integrable one. And then the standard Ortonian one carries some Kähler structure in this generalized sense. That means the closeness to the Kähler form is modular the torsion tensor of integrability. And so he's said that you have openness and then you have closeness. So that means that there's no complex structure for S6. Now, there are still essential insurmountable difficulties in this method because the global deformation of Kähler manifold may not be Kähler at all, just a regular one. Now, coming back to the question of Kodara and Spencer for PN, in 1989 and then later with the Erector in 1992, it was proved that PN cannot be deformed. So a natural follow-up problem is whether any reducible compact Hermitian symmetric manifold is globally non-deformable. So it means that if you have a family of compact complex manifolds over the open unit disk, and every fiber except the center one is known to be biholomorphic to Y, then you want the center fiber also biholomorphic to Y. So a compact Hermitian symmetric manifold, of course, simply means a compact holomorphic complex manifold with a Hermitian matrix so that for any tangent vector at any point, there's a biholomorphism which fixes the point and sends the tangent vector is negative. Okay. And if the manifold cannot be decomposed into the product of two such manifolds, then it's known as irreducible. The rank means the maximum dimensional abelian subgroup of the isometry group. So there are 6 types of irreducible compact Hermitian symmetric manifolds, as you can see from the list here, with the specification of the dimension and the rank. Okay. And the geometric description of the first type is the Grassmannian. And the description of the 4th type is the complex hyperquadric, which means the sum of the squares of the homogeneous coordinates in a projective space being 0. Yeah. The case of hyperquadric was proved by Junmuk Wang, which also was mentioned, in Ngaiming's talk. However, the case of a general irreducible compact Hermitian symmetric manifold remains open. And under the additional assumption that the family is a family of compact Kähler manifolds, then the global non-deformability of irreducible compact Hermitian symmetric manifolds was proved by Junmuk Wang and Ngaiming MOK. So in a series of papers, they introduced a completely new and very powerful method called the varieties of tangents of minimal rational curves. Each such variety is the set of all tangents to minimal rational curves passing through that point. And then they apply this method to a very fruitful study of uniruled projective manifolds. And in particular, they proved the global Kähler non-deformability of any irreducible compact Hermitian symmetric manifold. That was published in 1998. Now, here is a very simplified discussion of the proofs of the known cases. When minimal rational curves in a general fiber approach the center fiber, they may decompose into several branches of rational curves. If enough of them remain irreducible and retain the crisscrossing property of minimal rational curves, then you can verify that the center fiber is Hermitian symmetric. So when all these fibers, including the center fiber, emits a smooth family of Kähler matrix, the minimal rational curves from a general fiber could not decompose into branches in the limit, because there's a Taylor metric and it's already minimal in area or volume. So for PN hyperquadratic, one uses some special holomorphic vector fields on a general fiber whose integral curves are minimal rational curves. So minimal rational curves are still used. So for example, you take for PN, the Euler vector field in affine coordinates. Yeah. And then the different affine coordinates will yield different Euler vector fields. And when you look at an Euler vector field defined by the hyperplane at infinity for a general fiber and defined by an origin in the general fiber, you could normalize it by taking a constant multiple. And then if you normalize by the parameter raised to a certain positive power, you can always get a limit. But of course, the trouble is that when you get the limit, you have degeneracy in the center fiber. But in the case of projective, you can still use different Euler vector fields from different hyperplanes and origins and so forth, and you can conclude that there's still some crisscrossing. That means some non-integrability of the foliation. And you would get a result contradicting the fact that the Picard number of Pn is 1. That means there's only a primitive generator for all the line bundles. And the argument for hyperquadratic follows similar lines, but far more complicated. So in this talk, we are going to introduce a completely new method of proving the Grassmannian case. It's a technique to guarantee the extendability of certain special vector fields, like the Euler vector fields, from the general fiber to the center fiber, without reparametrization by positive powers of the parameter. Because the main trouble is that you had to reparametrize by power of parameter to make the limit exist just from normal family arguments. But then the limit would be useless. Okay. So we introduced a new method to make sure that such vector fields could have a limit without the reparametrization. And this method will work for the remaining cases with some modification, but we are not going to discuss the remaining cases. And this method is still being refined to try to get a better formulation. Now, you take an irreducible compact emission symmetric manifold. It carries with it many canonically associated holomorphic objects. In a holomorphic deformation globally, these holomorphic objects may become degenerate in the center fiber after some reparametrization. One would like to select effectively a collection of such objects so that even when they degenerate in the global deformation, the remaining properties and relations will still force the global deformation to be Hermitian symmetric. The minimal rational curves and special vector fields like Euler vector fields are some of the canonical associated holomorphic objects. And this new method simply selects some other canonically associated holomorphic objects. Okay. Now let me say something about the historic background of minimal rational curves. Frankel conjectured in 61 that every compact Taylor manifold positive bisectional curvature is by holomorphic Pn. And it was confirmed in a paper that I wrote with Yao around 1980. The method is to use curvature condition to produce minimal rational curves by minimizing the energies of maps from the true sphere to the manifold, and by deformation obtained enough of them in a crisscross manner to conclude the manifold is Pn. Mori used Frobenius transformations in characteristic P and the method of band and break to produce minimal rational curves under only the condition of positive anti-canonical line bundle, which proves in particular the Hashwan conjecture of character in Pn by the ampleness of the tangent bundle, which actually is a stronger algebraic geometric version of the Frankel conjecture when it came out in the Annals in 1979. Mori's technique actually was the starting point of the minimal model program. We would like to point out also that in a series of papers, Ngaiming MOK combined the algebraic methods of Mori and the analytic method from differential geometry to open up an entirely new vista in the complex manifold theory of semi-positive bisectional curvature. He completely resolved the generalized Frankel conjecture beyond its original formulation. And his pioneering method ushered in an important new direction of research. And in a series of papers, for example, you could read about it in this survey talk he gave. Now let's talk about this new method of introducing something else. The new method involves jet differentiation and eigenfunctions. So I'm going to explain it first in the case of Pn, and then tell you how to do it for Grassmanni and so forth, okay? Because it's easier to see it in a more transparent way for Pn. When you take the line bundle L, which is the primitive generating positive line bundle on each fiber, and together they would form a global holomorphic line bundle on the whole family. And you take its m power and get sections. And they have limits, okay? You could get the limits by looking at the zero direct image of the line bundle over the family. And then from that, you can get the limit at the center fiber. But of course, the limit in the center fiber may not be equal to the sections of the power of the line bundle on the center fiber. The limits would be only a subset in general. Of course, in the general fiber, they would be the same. Now, for biholomorphisms, we obtain the limits after we take the direct image. And in the case of m equal to 1, that means actually the primitive line bundle, we get the n+1 sections. Okay. And then we could take the vanishing of the S0 to be the hyperplane section. And then we could get a holomorphic family of origins by replacing each Sj by a constant times S0. Okay. So without loss of generality, we can assume that in the limit, we can take the first one to be S0m. Okay. And then we take the quotient. The quotient would vanish at the origin for every fiber, okay, including the center one. But for general fiber other than the center one, each Pj, this quotient, is a polynomial degree m on the affine part without constant terms. Okay. And you can decompose these affine polynomials in homogeneous parts. And then look at the action of Euler vector field. And the Euler vector field would act on them, of course, would act on each individual components, and then we get the coefficients. The kth homogeneous degree of the k to the power L, if you add L times. Okay. And then you can actually solve for Pjk from this set of equations. And a determinant in a denominator would be the Fenelon determinant because of these kj's, and it would be non-zero. So you could actually solve for the homogeneous part by using Cramer's rule and get the right-hand side here, sticking into the Fenelon determinant. And then your original affine polynomial, which is the sum of the homogeneous part, can now be written as a sum after you divide by the denominator determinant. Okay, And when you expand it, according to this column here, you should get some constants, and then the action of the Euler vector field raised to power on each pj. And you now look at this part before the action. And this part would give you an mz differential operator. It's a C-linear combination of the Lth iterator action of each j. So this would be a higher order differential operator. And more or less, it's like the Euler vector field, but now you reject differential operator. And then each of the affine polynomial actually is an eigenfunction for this higher order jet differential operator with eigenvalue 1, because that's how we get it. So each pj would be expressed in terms of this, which is written as a linear combination. Therefore, each of the pj actually is an eigenfunction with eigenvalue 1. Okay. Know that the Euler vector field itself is only meromorphic on X without normalization by a factor of t to the power nu for some non-negative integer nu. But here's the main point. We could look at the center fiber as a Moiseson manifold because the deformation of the irreducible compact emission symmetric manifold, which of course is algebraic, but the limit may not be algebraic, may not be Kähler. Otherwise, the Kähler non-deformability would cover it already. But we know it's only a Moiseson. And it's Moiseson with respect to this line bundle, the primitive line bundle L on the whole family. So when you raise this to a certain high power, then the limit of sections would be enough to give the Moiseson property, so that you can actually argue that the affine polynomials would form local coordinates at most of points. That means outside a certain subvariety, you would be able to form local coordinates. But those affine polynomials are eigenfunctions with eigenvalue 1. Therefore, you know that this one, which may not be holomorphic, but we know it's meromorphic. However, it acts on the limit of the eigenfunctions to give you eigenvalue 1. And the eigenfunctions here can form local coordinates at most of the points. So therefore, this jet differential operator actually is holomorphic at most points. And by Hartogs, we know that this thing actually emits a holomorphic extension. Yeah. So after you get the holomorphic extension, you can conclude that the original Euler vector field has holomorphic extension without modification by t raised to a certain power. Yeah. Otherwise, when you look at the affine coordinates, you cannot get the eigenvalue 1. So this shows that the regular Euler vector fields actually extend to the center fiber without reparametrization, without renormalization by powers of t. And the Euler vector fields on the general fiber can generate a Lie algebra of holomorphic vector fields. And then the trouble when you have to normalize with powers of t is that structural constants of the limit would be different. But if there's no renormalization by positive power of t, the structural constant in the limit also will be the same. So the same Lie algebra or Lie group acts on the center fiber to make it Hermitian symmetric. So this is actually a very simple idea, but it points out a new direction of doing it. Okay. Now, what is happening with the limit of the global sections on the center fiber? And I'd like to make one remark. We actually use a zero direct image of the power of the primitive line bundle to help you get the limit. Actually, you don't need to do it. You can actually always get a meromorphic extension, and then you just normalize with certain power to get the extension. And then if after normalization to get the extension, if the result is not linearly independent, you can get a linear combination, and then there you can also divide by a certain power. And this way is a more direct, naive way of getting the limits. Now, let's look at the situation of the Grassmannian. What happens there? Now, first, the Grassmannian, just like the hyperquadrics, they are naturally embedded into some projective space in a minimal way. And when you look at Euler vector fields in the hyperquadrics, let's see what happens there. Let's look at a simple case when the dimension of the hyperquadric is even. Then you can rewrite the quadratic equation in this form. So it's just a product of adjacent homogeneous coordinates. And then you divide by one of the coordinates, you get something of this form, okay, which is representing a hyperquadric. And for this, you can get a Euler vector field or Euler-like vector field. Actually, it's not an Euler vector field, but it has the property of getting eigenfunctions. So what you do is that you take this first one and do it the same as usual vector field. And for the others, they come from a pair. And for each pair, you take one. Okay. So you have different ways of doing it. You have this boldface J, which tells you which one to take, whether to take the even one or the odd ones here for each one. And then they would give you a vector that is tangential to the hyperquadric. This is a horovector field on the ambient projective space, but it's not the usual Euler vector field. And this is tangential to Qn. But it would admit each of these Z1, Z2, etc. as eigenfunctions. And you can also add two of them up and so forth because they are different choices. And if you add up all of them, you get this one. Add up the even choice and the odd choice, you get this one with a 2 here, of course, because this is the choice of even and odd. And there, you can use this one. This one also has certain eigenfunctions. And the main point is that the integral curves for this Euler-like vector field, they are not minimal rational curves. You can easily construct one that is not, like n equal to 5, z1 equal to minus tau squared, and then z2, z3 equal to tau. The minimal rational curves will be given by linear things. Okay. And what are the eigenfunctions for this Euler-like vector field here? Okay. It is homogeneous in Z1 and Z2 square. This is a misprint. C2n square. So you take a monomial like this, and so Z1 occurs by itself, Z2 square. Then you add on it, you get this, and it is an eigenfunction. So the whole point is that when you look at such situation like the hyperquadric, you can actually get Euler-like vector fields. And then you have also to look at homogeneous, not just the homogeneous ones, but any affine polynomial in these variables, and then decompose in homogeneous components, and then use Cramer's rule to get a higher order jet differential. Now, in the case of Grassmannian, it's something analogous, except that is not defined by one hyperquadratic. It's defined by quite a number of hyperquadratics, and it's not a complete intersection. So suppose you have CK inside Cn, then you fix k minus 1 indices, and then take k plus 1 indices, and then you can take the Krüger coordinates as determinant of k of them. And here, when you take k minus 1 index, and then you have k plus 1 index, you can remove 1 and stick it here among the k minus 1 indices, and then get the sign correct. And these are the hyperquadratics whose intersection would give you the Grassmannian. So you do the same kind of thing. Again, you take the affine situation. That means you fix one of the Krüger coordinates to define the infinity, the intersection infinity hyperplane with the Grassmannian, and then you get the affine coordinates. And the Euler-like vector field would be the same as the usual vector field, Euler vector field, except that there's different constants. It's the same as the situation of the hyperquadratic when you have a different constant here. Okay. So in the case of the Grassmannian, also you get different constants. And so if you take different constants, you get this. You choose the constants correctly. Okay. So what are the constants, these gammas and so forth? Gamma L1, Lk would be the number of elements in L1, Lk, which are not inside 1, 2k, 1, 2, 2k. Okay. So you fix one, the Krüger coordinate 1, 2, and so forth to k, and use it to define the infinity. And then for other coordinates, you just find the number of elements which are not inside this. And then you put it here, and then you get an Euler vector field. And so when you take the affine, the analog affine polynomials, you take polynomials in this variable. And this variable is the Krüger coordinate raised to this power qi1ik, which is the mkn is the least common multiple of all the gammas, and it divided by the gammas. Okay. It is just a very logical way of doing it. Okay. And let me say something about the jet differential operators. Okay. This method exploits the setting of deformational manifold so that the limit is still regular. And for regular manifold, instead of just using tangent vectors, you can use jet vectors. You can use higher orders. And a similar use of higher order jets was introduced in the hyperbolicity problem for a generic hypersurface high degree. Okay. And then that actually is the reason why I directed my attention to using a jet differential, because I used them once in the hyperbolicity problem. Okay. Compared to the use of jet differential operators in other contexts, one new special feature of this use is the special class of jet differential operators, which are constant coefficient polynomials of Euler-like vector fields, and which emit sufficiently many special eigenfunctions or eigenvalue 1. Here's the main point, that this method not only uses the jet differential operators, but those obtained as constant coefficient polynomials of powers of Euler-like vector fields. And then they emit many special eigenfunctions of eigenvalue 1. They are special, but their limits would give you the Moissan property of giving local coordinates at a general point. Yeah. And now I think I still have just a little bit of time. I can actually stop here already, but I just want to tell you what happens in specific cases so that you can get a better idea what's going on. when you have a two plane in C5, then of course it's spanned by two 5 vectors, and then the pure coordinates would be like getting 2 by 2 matrix and determinant, and then the quadratic relations defining the Rashomon would be like this, okay, and then there are 5 of them, and then the coefficients, which counts the number of indices not in the index set defining infinity, would be like this. It's very explicit, so you can get the vector field like this. Yeah. And so here would be the coordinates, and you get polynomials in the coordinates with the correct homogeneity. Yeah. I think I'll stop here. Yeah. And thank you for your attention.
Okay. Thank you, Professor Siu, for giving the very nice talk. We are going to meet Professor Siu again in the roundtable discussion later on. So our second invited speaker is Professor Wai-Ping Lee, who is currently a chair professor at the Mathematics Department of Hong Kong University of Science and Technology. Professor Lee obtained his PhD degree in 1991 at Columbia University and came to join the Hong Kong University of Science and Technology in 1992. His research area is algebraic geometry. Professor Lee was awarded the ICCM 2017 Gold Medal of Best Paper Award, and also 2021 Higher Education Outstanding Scientific Research Output Award First Class from the Ministry of Education of China. So now may I invite Professor Lee to deliver his invited lecture.
Okay, thanks for the invitation. It's a great honor to speak at this occasion. I came to Columbia in 1985, the same year when Professor MOK came to Columbia at the same time as a faculty. I was a student. I think impact of Professor MOK's presence at Columbia was immediately felt because many of my classmates went to his classes and eventually became his PhD students. And another thing, when I first came to Hong Kong, in fact, probably I'm the only algebra geometer in Hong Kong. When MOK came here, very few geometers in Hong Kong, and Professor MOK initiated Hong Kong Geometry Colloquium. At that time, very few activities around and very few visitors to Hong Kong. So it really keep us going. And the impact is definitely felt at that time. So I will talk about the enumerated geometry on moduli spaces. In fact, we heard a little bit about moduli spaces in Professor MOK's talk, and also counting. But in MOK's talk, counting of numbers, here we are counting about the geometry. So it's called enumerated geometry. Okay, so what is enumerated geometry? It's a research area where people study counting of various geometric objects, such as, so this is known in even not high school, elementary school student, given 2 points on the plane, there are only one line passing through 2 points. So the geometric object is this line, only one line. And then there's a condition passing through two points. Okay. So that's the baby version of enumerated geometry. Okay, so in fact, enumerated geometry came to mathematics a long time ago in Greek time. Okay, so this is a famous problem. Apollonius, about 2,000 years ago, proposed the following problem. In fact, he solved this problem. For high school students, you can understand this problem. Given 3 circles, how many, and also to construct circles tangent to a given 3 circles, how many circles are there? Tangent to the given 3 circles. So if the given 3 circles are general position, the number of circles tangent to the 3 circles, in fact, is 8. There are 8 many. But if you rearrange special arrangement of given circles, the number could be an integer from 0 to 6. But anyhow, we can see the innumerable geometry already exists 2,000 years ago in this Euclidean geometry. Okay, so now I talk about projective space. We heard about this also several times, but I will go to very elementary stuff at the beginning. So we knew Euclidean geometry studies geometric objects in R2, R3, etc. Rn. But algebraic geometry studies geometric objects in projective space Pn. So what's a projective space? So basically, we heard about this, but let me say it again because some people may not geometers. So it's just a collection of such things, right? In fact, this is equivalency relations. Okay, so lambda times lambda is not 0. Then we consider them to be equivalent. But this cannot be 0 simultaneously. So that's projective space. Okay, so these points are called homogeneous coordinates. All right, okay, so if these numbers are integers, are not integer, real numbers, so projective space we call Rpn. For example, Rp1 is a circle, topologically. Rp2 is a union of R2 with Rp1 with a circle. But if you take the points to be C in the complex numbers, then projective space will be denoted by Cpn. As Professor MOK mentioned, that the complex numbers is crucially important in mathematics. So Cpn is a two-dimensional sphere. So this is something we knew. And Cp2 will be a disjoint union of C2 with the Cp1. You can see from here why they are disjoint union. You just minus this, delete the Cn, and you get a Cpn minus 1, because the Cn will be embedded in Cpn by these coordinates. You just take the first coordinate to be 1, and then the other coordinate can be arbitrary. Okay, so the first golden age of innumerable geometry, in fact, is near the end of the 19th century. The key mathematician is Herbert Schubert, is a German mathematician. And many innumerable geometry problems can be rephrased as intersection theory on the set of geometric objects. So the set of geometric objects usually called modular space. Okay, so this is set up. Okay, so let's look at an innumerable geometry problem. It's really very typical to something I'm going to talk about. So let's ask this question. How many conics tangent to 5 given lines? Conic just means a geometric object. Now we are in a projective space, okay? So it will be geometric object, so it will be projective space, P2, so 3 variables. And conic is just 0 locus of all the points that satisfy this equation. Okay, so it's a homogeneous of degree 2, so called a conic. Okay, so then let's look at the set of conics. In fact, it's P5 because set of conic will be A, B, C, D, E, F, 6 variables. But you modulo the equivalence, so that's exactly P5. By my introduction. So therefore, this will be called a modular space, right? The set of geometric object is called a modular space. So our modular space, in fact, is P5. And each C curve will correspond to an element in P5 with their coefficients. So their coefficients will correspond to this C. Okay, so let's look at the simple problem, simpler problem than this problem. The simpler problem is the set of conics passing through a given point. Okay, so we know the set of conics passing through a given point, in fact, is a linear subspace of P5 because you just plug in the points into here, you get a linear equation, ax squared. X squared is just a number plus b right? You get a linear subspace of P5. Then if we ask, given 5 general points, how many conic passing through these 5 points? So we know there are only 1 because it's just intersection of 5 linear subspaces in P5, right? In P5. So clearly now we can see what I said. right? Enumerated counting becomes intersection theory on modular space. So the condition that conic passing through a point becomes a divisor or subspace in a modular space, and then we intersect these five subspaces together. We get the intersection number is 5. It's 1. Okay, so you can see it's intersection theory on modular space. Okay, so now back to my original problem. So it's a little bit harder than the problem of passing through a point. So tangent to a line, this condition, tangent to a line, conics tangent to a line is a quadratic condition. It's not a linear condition. Therefore, the set of conics tangent to a given line, in fact, it's a quadric in P5. Okay? So therefore, we have 5 quadrics because we have 5 lines. Then we want to intersect them. So you can see naively, you will get 2 to the 5th power should be 32, but the answer is wrong. Why the answer is wrong? The reason is the intersection of 5 conics for 5 lines, in fact, is not a finite set of points. Okay. The reason is, even though these lines are general, but this conic are not general. Because what is a tangent? Tangent means your line, the line intersects your quadric with a multiplicity 2. So if your conic becomes degenerate, so we can have degenerate conic, right? Ax plus by plus cz squared equals 0. That's a degenerate conic. Any line passing through this conic, of course, with the multiplicity 2. So therefore, in a quadric, will contain the set of conics, which is a surface. You have ABC here, surface, which is a two-dimensional surface. So therefore, the intersection of 5 conics contains a surface. It's not a finite number of points. And this type of intersection is called excessive intersection, right? We also saw in the previous talks. So therefore, so what is intersection theory? So-called supercalculus. Intersection theory basically develops a method to deal with this type of situation where you have excessive intersections. The dimension is not correct. Okay, but if you do that, you use the standard method, you will find out that the actual number of conic tangent to 5 equals 1. Okay. Okay, so now let's talk about the question we are interested in now. So now we are interested in a degree 5 hypersurface P4 called a quintic. For example, given by this degree 5 equation with the 5 variables in P4. Clemens conjectured that for a general quintic K, quintic X, there should be a finite number of rational curves on P1 of fixed degree on X. It's similar like Professor Mo talked about counting points, rational points on general a curve of genus bigger than 2. The conjecture is still open for larger degree. So this conjecture is not proved so far. But anyhow, let's see if we know it's a finite number, let's count. The counting of number of rational curves for small degrees was done by mathematicians like Sheldon Katz using the standard techniques in intersection theory. For example, the number of lines, degree 1 on general quintics is 2,875, and the number of conics, degree 2 on the general quintic is this number. Okay, so now turns out that there's a counting by physicists. So in a seminal paper by a physicist, a Candelas, so right now is very famous, De La Ossa, Green, and Parks in 1991, the number of rational curves of all degrees on quintics X, in fact, is calculated using a physical conjectural technique, even it's a conjectural technique in physics, called mirror symmetry. I think people heard about mirror symmetry. Now mirror symmetry basically coming out of this, this work because of importance. How did they do it? Okay, so this NGD represent the number of genus G, degree D curves on X. Then you write a generation function, put a auxiliary variable Q here, put a degree D here, and the G is fixed. Okay? So what they did was they, in fact, construct another Clavion threefold called X hat, called the mirror, and then study the moduli space of complex structures on X hat, and then computed some period integrals. We heard about period in the next talk. And using a string duality, so this is the physical duality, conjectural duality, to predict and also conclude an explicit formula for F0Q. The first few terms of this X0, in fact, correspond to the rational curves of small degree that mathematician computed before. So it agrees with the computation by mathematicians. Okay, but anyhow, so physicists computed enumerative geometry on X by a non-enumerative computation. Also on another manifold, on the mirror, not on X. Okay? But the mathematicians still want to do enumerative geometry on the X instead of non-enumerative computation on another manifold. So in order to do that, however, mathematicians have to make several changes to original enumerative geometry problem. So this is what I want to emphasize. So the mathematicians, when they try to solve a problem, they always change the problem or extend the problem. Along the way, new techniques appear. So recall the conjecture of Clemens. Remember that Clemens' conjecture is yet to be proved. So therefore, we don't know whether the number of rational curves on a general quintic is finite or not. Okay. Furthermore, mathematically, the modular space of curves on X is very hard to work with. For example, Professor MOK, this modular space of minimal tangent, minimal degree, this also type of modular spaces. So in some cases, you can work on it, but in some other cases, it's very hard. Okay. So what do we do? So this is the first change by mathematicians. So instead of counting curves on X, we can count the maps from curves to X. So we changed the problem, in fact. We can count the number of maps from curves to X. Now, in some special cases, for example, your curve is rigid. We also saw the rigidity here, no deformation. And if the map is isomorphic, then the counting the number of such maps is the same as the counting number of such curves. So it's a generalization, but it's a vast generalization. Okay. Now, the set of such maps are called the modular space of stable maps to X. It's defined by conservation. And so now we see the modular space. Okay. So we denote this modular space by MGXD. So G for the genus of the curve, D for the degree, where G is the genus of the curve, D is the degree of the image of this curve in P4. Okay, so modular space is set up. Again, a problem appears. The problem is the modular space is not compact. Therefore, you cannot perform intersection theory. Okay, we knew intersection theory cannot be performed in a affine space. For example, you can have two lines parallel, intersection 0, but you can have another two lines intersect, intersection is 1. Then you have a problem that y equals 0. Right? That's the problem. The problem comes from the space is not compact. You have to make it compact to have a meaningful intersection theory. Okay, so there's a solution. Again, Kontsevich introduced stable maps from nodal curves to X. So you change your definition domain. Instead of a Riemann surface, you change to a singular Riemann surface. So the domain of the map now may not be a singular curve, but it is at worst a union of smooth curve intersecting transversely. So these type of curves are called nodal curves. Then you just add, by adding these maps to the modular space, you enlarge this modular space. So this turns out it can be proved that this modular space is compact. Okay, so this is the second step. All right, so then we'll continue. Now,
Yes,
usually,
thank you, Professor.
this
You
modular
can share
space
screen
has
now.
a dimension.
Good,
the
good,
dimension
good. Yes.
is expected to be 0. We saw this also in the previous talk. And rigorously, by definition theory, the expected dimension of this modular space is in fact 0. However, the actual modular space is not 0. What's the reason? It is due to the similar phenomena mentioned in the problem of counting number of conics tangent to 5 lines in P2, exactly excessive intersection. Okay, so this excessive intersection appears all the time. So how do you overcome this difficulty of excessive intersection? You say, there's the intersection theory already there, but this is not a modular space of a classical intersection theory. This modular space comes from kind of a modular problem. Okay, so the modular space is equipped with the so-called deformation and obstruction theory due to the work of Junli Tiangang and Karen Fataki. There's a method called the method of perfect obstruction theory is developed. Now you can see that this is exactly what I want to emphasize, that we change the problem, we try to solve this very classical problem. Yeah, this is a very simple problem, right? Looks like everybody can understand what we are trying to do, but turns out that it's very hard to do, and we change the problem to counting stable maps, and then with that, we can we need to develop new methods. Okay, so old method does not apply. So-called the classical enumerated geometry problem does not apply. So they create something called a perfect obstruction theory. So this perfect obstruction theory will define something called a virtual cycle. So it's not
Professor, if you don't mind, you can you tilt down a little bit your webcam?
And also sits in the modular space. Therefore, you can calculate the degree of this this virtual cycle, and that will be defined to be so-called Romo weighting invariance, NGD, I mentioned in the very beginning. Okay, but this number, since we change a lot, this number, in fact, is actually not real counting, it's a virtual counting, because, but sometimes you can see this number is a rational number. It's not integer. So the problems changed. All right, anyhow, so how do we
Hello,
compute,
Professor. Did you hear me?
Yes. Do you hear me?
Yes, we can. And but your webcam can you tilt down a little bit because your face is yeah, good.
The modular space M0, in fact, this modular space is smooth.
Is it okay, sir?
Yes, good.
And the virtual cycle,
I don't see the speaker.
Yes.
Okay.
Good.
All related. So before many years ago, Atiyah and Abad developed a theory
Thank you, Professor.
Localization, which can be used to compute Chern classes using this virtual class, this torus action. Because this torus action will have a fixed point. Atiyah-Abad theory says you just calculate some computation. You just do some computation over the fixed points. So that's much easier. However, our setup is virtual. It's not Atiyah-Abad original method. Does not apply. Again, mathematicians found a way to generalize Atiyah-Abad method. So Graeber and Panda developed a virtual torus localization method to deal with virtual cycles. Okay, so then this is what we did as mathematicians. So Gimintal, Liang, Liu, and Yao carried out the computation of A0 using the virtual localization method I mentioned. Okay, so in fact, the virtual localization gives a vast amount of combinatorial data So this process is not difficult. You just apply a Graeber pattern localization formula, you will get a vast amount of combinatorial data. The physicists have explicit formula for F0. So therefore, the key is, one of the challenging problems is how to package this combinatorial data into a neat formula, a formula that the physicists found. So therefore, there's a method or many methods developed to do so. Is very sophisticated and also becomes the standard method for higher genus and other target manifolds. Okay, so this is for F0 is done. So how about the higher genus chromovitin invariance of the quintic? For higher genus, the modular space is no longer smooth. So therefore, the original method that worked on the smooth manifold failed. Again, another problem. The virtual cycle is no longer Chern class of some vector bundles. So it turns out that these vector bundles for higher genus becomes not only sheaves, not vector bundles anymore. So therefore, you need new methods. Okay, so I'm involved in my research recent years involved of this part. So there are great progress of higher genus, including physical, means physics did a lot of work, BCOV, and also mathematical results. So along the way, many new methods and viewpoints have to be developed to understand higher genus chromovitin invariance. So I don't have time to talk about this part because it takes maybe another half an hour. But anyhow, I try to give you an impression that the original problem, which is naively simple, like this, and led to an area of mathematics that's very deep and has impact on other areas of mathematics, which means the methods or the concept developed here can also be applied to other parts of mathematics. So this is how mathematics goes. And maybe I just, let me see, my time. Yeah, I think probably I just stop here.
Thank you, Professor Lee, for giving the very nice talk. So our last invited speaker is Professor Gisbert Woesthoff, who is Professor Emeritus at ETH Zurich. Professor Woesthoff received his PhD at University of Heilbronn. And then before becoming a chair in mathematics and ETH, he worked at Max Planck Institute of Mathematics and also University of Wuppertal. Professor Woesthoff is internationally known for his fundamental contribution to number theory and arithmetic geometry. He is a member of the German National Academy of Science, Leopoldina, the Berlin-Brandenburg Academy of Sciences and Humanities, of the Academia Europaea, where he was the chairman of the math section for a number of years, and of the European Academy of Sciences and Arts. In addition, Professor Woesthoff delivered an invited address at the International Congress of Mathematicians in 1992. So the title of his talk is Periods of Integrals. So may I invite Professor Woesthoff to deliver the lecture.
So thank you for inviting me to this very nice event in honor of Professor MOK, whom I know already since many years. Actually, we met the first time in Wuppertal when I was a postdoc. And since then, we very often met on diverse occasions. So in particular, when I visited quite frequently Hong Kong University and Hong Kong University of Science and Technology. We always talk to each other, and it was a pleasure to be in contact with him. And I would like congratulate Professor MOK for this wonderful prize, and I hope he can continue with such great mathematics. I'm a student of Theodor Schneider, who was mentioned already before in Freiburg. He solved one of the Hilbert problems, and so I got very early in contact with transcendence and the problems in transcendence. So, for instance, elliptic functions, values of elliptic functions, and so this interest continued during all my mathematical career. So one of the deep problems is whether periods of integrals are transcendental or not. Now it is a very difficult problem to prove that a number is transcendental, because by definition, transcendental, you have to prove that if you plug it into a polynomial with integer coefficients, then it should be non-zero, and so you have to solve infinitely many problems and or calculations, and this is almost impossible. So the method in transcendences are in general indirect by contradiction, and so this is how many numbers were shown to be transcendental. I report on a very general method which covers a lot of questions, and we will see the context. So the general setting is you take a projective curve of genus G over a number field K. We can associate two vector spaces of dimension 2G. The first is the so-called Petty homology, which is a vector space over Q with basis, you choose a basis C1 up to C2G. And the other one is a vector space of holomorphic differential form, the Ram cohomology, which is a vector space over K with basis Xi1 up to Xi holomorphic ones, and eta1 up to eta G, the meromorphic differentials, which have no residues. So there is a pairing between these two vector spaces going to C just by integration of the differential form omega over the enclosed path C. And this is called the classical period. It is known that if you tensor with C, if you extend coefficients to C, then there is an isomorphism between the dual of the Bethe homology and the Ram cohomology. This is a very important isomorphism. Now you can associate to this situation the vector space generated over Q bar by the periods of X. So these terms. And a second one, which is very important also, if you add the number 1. Let me give you some examples of this situation. So the simplest example is to take the GM. This is a curve, although not projective. this is, as we shall see, a small problem. You have this logarithmic differential, and now you can attach a period in this sense. The example 2, this is an elliptic curve given by this equation, and this should be a plus sign. And here the psi, this the holomorphic differential, is dx over y, and the second one is dx over y, which is second kind, and which is meromorphic. So you can take C1 and C2 as closed cycles. C donut you had already seen, or Professor MOK had already mentioned this. And so if you calculate the dimension of it is shown, it can be shown that the dimension of P of X is 5 or 3 depending, and this means that the periods are transcendental. So this is part of the work of Schneider. The third example is you take hyperelliptic curves given by an equation y squared is equal to P of X, where P is a polynomial with coefficient in Q bar without multiple roots. So I specialize this example for degree 5 or 6. The degree of P of X is 5 or 6. The Doram cohomology has a basis of dx over y and x dx over y, holomorphic differentials, so first kind, and x squared dx over y and x cubed dx over y for the second kind. They don't have residues. The Betty cohomology has a basis C1 up to C4 of closed paths, which you can imagine. In this case, the genus is 2, so you have a donut glued together, and you can consider the various closed cycles. And so in this case, you have also this period. And in this case, we also consider the space P of x1 generated by 1 and P of x over Q bar. And so the natural question are, these are both vector spaces over Q bar. And the question is, what is the dimension of P of x and P of x1? In other words, are the periods linearly independent, or are there dependence relations? And if so, you could ask, what are the relations? And for instance, are they motivic? Do they come from geometry? So the first result in this direction was, or the first question in this direction was the question by Siegel, who asked for this integral and the x over 1 plus x cubed, and asked whether it is transcendental, or what is the same, whether the three complex numbers 1, log 2, and log minus 1 are linearly independent over Q bar. So this is a linear form in logarithms. And this example can be viewed as a starting point for Baker's theory of linear forms in logarithms, the qualitative theory of Baker. So Baker's theory splits in two parts, or two different aspects, namely the qualitative part and the quantitative part. So I'm looking in this lecture only for the qualitative part, and so I have to go back to this to the number 2 pi I, which is integral dz over z, which does not fit in the theory so far exposed by the following reasons. GM is not compact. GM is A1 minus 0.0. dz over z is neither holomorphic nor without logarithmic singularities on C. And what causes the most problems, the path of integration is not closed in the case of log alpha for alpha different to 1. Here we have alpha is equal to, we can take alpha as minus 1. So one of the big questions, or the questions, is that non-closed paths can be also included in the theory, and this is an essential part of the theory. So the first thing is one has to study something, the Jacobian of the curve. So there exists an abelian variety A equals J of X, and a morphism from X to the abelian variety. So that the following conditions are satisfied. This pair, V de Ram and V Betty, are isomorphic to the same quantities for the abelian variety. And this can be achieved. In other words, and even more generally, we may transfer the questions to general commutative algebraic groups G, and not necessarily compact curves X dashed in X by taking just the Jacobian. So we have to study commutative algebraic groups, and such a group is an extension of an abelian variety, and we have also already seen that it is a quotient of C to the n by a lattice. By a linear algebraic group, L equals GA, the additive group, and to some power GM to the L to some power. Here we assume that we have assumed that field of definition is Q bar, so we can split the linear group. So there is a fundamental theorem which very much governs the theory. Such a G is an extension of an abelian variety by a linear group. So we have such an exact sequence with L linear and A abelian. So Baker's theory on linear forms in logarithms deals with the very special case of torus D equals Gm to the n. So he only considered the linear part in whereas the abelian part does not fit in Baker's original theory. So, So we have somehow, yeah. So on the one hand side, we have an algebraic group with tension space T0 in the neutral element, which gives an algebraic pair of this type. On the other hand, if you look at the complex points on the algebraic group, this is a Lie group, its tangent space is a Lie algebra, and there is a uniquely determined complex analytic homomorphism, the exponential map from the Lie algebra to the complex Lie group. And this is this gives you an analytic datum and of this form. The whole story is to somehow compare the analytic structure and the algebraic structure, and using analytic maps or analytic GM example is here we have the exponential, this classical and exponential function, z goes to the e to the z, and this leads us immediately into the theory of Hermite and Lindemann. Hermite looked at z equals 1, and Lindemann first at z equals pi I, and then this leads to the transcendence of 2 pi I. The second example is a abelian variety in the simplest case, namely an elliptic curve. Here we can express the exponential map very easily with the help of the Weierstrass P function and its derivative. So in both cases, we have functions which take transcendental values for, so transcendental functions which take transcendental values for Z algebraic in general, up to some exceptions. So this is a general principle. A transcendental function or map should map an algebraic point to a transcendental image, and so after a long search for extending Baker's method to commutative algebraic group, we solved the following problem. The first, let G be a commutative algebraic group defined over Q bar. We take its Lie algebra. Since G is defined over Q bar, the Lie algebra is also Q bar vector space, and we take a subspace B, sub algebra, which is also a sub-vector space because things are commutative. And then we take the image of this complex vector space BC under the exponential map of the group G. This is first, in general, Lie subalgebra, and we can look at the algebraic points on this transcendental subgroup, which is defined by taking B, the intersection of B, with the algebraic points on G. So the question is, are there algebraic points on B? And I proved in 1982 the following statements are equivalent. There are non-trivial algebraic points on the Lie subgroup B, and there exists a connected algebraic subgroup H of G with Lie algebra with non-trivial Lie algebra H contained in B. So if this happens, then if B of Q bar is non-trivial, there is an algebraic subgroup of B, from which we get the algebraic points lying in B. So a very striking example application is the following theorem: let Xi be a closed rational differential one form on a smooth algebraic curve, both defined over Q bar. You take a closed path on X, and then the period, the corresponding period, is either zero or transcendental. So, there are obvious questions. Can such a integral, such a period be zero? Or if so, can these cases be listed? And the question is, are they motivic? So this gave me a lot of headache. I knew that it can take the value zero, and there are geometric reasons for that. But somehow I was many years unable to prove that these are the only counterexamples for the period being transcendental. So let me give you some of the consequences of this analytic subgroup theorem. For instance, an old question already raised by Siegel is this Euler integral. Siegel and Schneider already got some very partial results on that, on the values of the beta integral. In particular, one can specialize, and then you get values of the gamma function with a pi as a factor. This is a period of this type, but the gamma value is assumed to be a non-period. This is a very open question. So the question is, in general, are all transcendental, all numbers periods, or are there non-periods? And so nobody knows at the moment whether there are examples for non-periods. For instance, E plus pi, or other very strange complex numbers. So using this analytic subgroup theorem and this integral theorem, one can deal with Leibniz conjecture on squaring an oval, which leads to elliptic and abelian integrals. And this was mentioned to me by Arnold when he visited ETH at Zurich. He discussed with me this question, and he mentioned that this is already has already been discussed by Leibniz, and so this problem can also be solved by this theorem on periods, which I mentioned before. So there is also a conjecture by Kontsevich and partly Zagier. They somehow classified the relations between periods of integrals for differential forms of higher weight, so the general periods, and they gave a list of relations which strangely enough coincide with the counterexamples which I found in long time before. In the case of weight 1, so periods of differential forms of weight 1, which I gave examples, and so using this analytic subgroup theorem, and one can prove Kontsevich conjecture for weight 1 periods. So this is the first result in the direction of Kontsevich conjecture, which is meant to be totally out of reach in general, and so it's an extremely hard problem. The next thing is what you can get there is what we can get with this analytic subgroup theorem are isogeny estimates. When I was when I was postdoc at Wuppertal, before I became full professor there, Faltings got an offer by Wuppertal, and he came to Wuppertal at the University of Wuppertal. And one day I asked him, what problems are you working? And he said, well, I'm working about Mordell's conjecture. I thought, oh, well, this is very ambitious, I think. So somehow I got very puzzled. But then he proved Mordell's conjecture, and one of the aspects, or one of the components, is a Tate conjecture. The Tate conjecture is something about isogenies between abelian varieties, which by known results lead to Tate conjecture. So in principle, we could have proved Tate's conjecture, but we were only second winner, so to say. We came too late. Tate's conjecture by transcendence. Tate's conjecture is somehow a linear form in periods on the product of the two abelian varieties, and the isogeny estimates deal with the problem to find relations between the periods of two different isogynous abelian varieties. So the next thing I came across was billiards on the ellipsoid. This is a problem in differential geometry, more or less. The question, a question on closed geodesics on the ellipsoid. There was work of Knörrer on this a paper of Knorr, which appeared in the Inventiones, and I realized that one can deal with this problem in an effective way by using transcendence of periods. So one can classify the closed geodesics on the ellipsoid, a well-known problem. So the original problem that the GM is not compact. This can be dealt with in a very conceptual way using the linear Swan motifs, and we have published a book together with Annette Huber in the Cambridge Tracts in Mathematics 222. 27, which just appeared this year, and there you can also get much information about the history and the problems which were solved by means of these essentially analytic subgroup theorem. Okay, so thank you for your attention.
Yeah. Thank you very much for your very interesting talk. We will start the roundtable discussion now. And may I also invite Professor Fu Baohua from the Department of Mathematics, Academy of Mathematics and System Science, China, to join the discussion, together with Professor Xiu and also Professor Wustos. Well, anyway, maybe we, because of the limitation of time, and also I think we will not have the roundtable discussion for 30 minutes. Instead, maybe 15 or 20 minutes. Okay. So we have a number of questions or topics that we want to discuss with the panel members. So so all these are sort of related to either interdisciplinary factorization or interdisciplinary factorization of mathematical research. So, so as you can see, we have this first question about interdisciplinary factorization. So, so the general question is how does mathematics transfer information within different fields of mathematics? So I think Professor MOK's work on this functional transcendency is an example of interdisciplinary fertilization. And Professor MOK, maybe you can say something about this.
Yeah, sure. So I think it has to do with also the atmosphere, also the avenues in which these ideas can be communicated. So I guess I learned about the Andreoff conjecture from Professor Wustos visiting the Institute of Mathematical Research. And the institutes or centers of research around the world are places where people can freely exchange their ideas, and sometimes also in different fields of mathematics. And myself, I like very much to attend the lectures of other fields. So it's through such an atmosphere of free exchange, and also in addition to that, also formulation of problems. So I was interested in number theory for a long time. And for instance, I did model V for complex function fields, and at that point, the avenue simply doesn't exist. The platform doesn't exist. The paper was published, but sort of very few people from the number theory community would pay attention to it. But then I insisted in some sense, and I went on in other areas. And I think the fact that I could, for instance, attend lectures and take part in conferences in other areas of mathematics helps.
Okay, so Professor Fu, I know that you originally worked in symplectic singularities and geometry of Fresnel manifolds, and has been using the VMRT in some of your recent work. Can you tell us how did this happen?
Thank you. So first of all, I'd like to congratulate Professor MOK for this prize. So in Chinese, so we say it's 实至名归. So in fact, I didn't know much about the VMRT theory only after my PhD. But I just know this, but not studied it carefully. Until in 2007, I met Professor Junmu Huang in a conference in Taipei. I explained to him one of my results on characterization of hyperquadrics. And then he got interested, and then he explained to me the work of Professor MOK on the recognition of hyperquadrics, or more generally, reducible Hermitian symmetric spaces from its VMRT. And only at that time, I really got motivated to study VMRT theory in detail. And then I worked at some small workshops in NUT. At that time, I was in NUT. And then I started to work with Junmu Huang. So VMRT theory is quite different from my previous research, which is on symplectic singularity. So, however, it turns out VMRT and symplectic singularity are quite related via the rational homogeneous spaces. And quite recently, in a joint work with Liu Jie, we have proposed a conjecture which gives a list of final manifolds of big number 1 whose tangent bundle has some positivity properties. In this work, I used both subjects, namely VMRT theory and also birational geometry of symplectic singularity. So I'm quite happy to have this work done. So all my congratulations to Professor MOK.
Thank you, Professor Fu. Professor Siu, I know your research interests involve interface of complex variables, differential geometry, and also algebraic geometry. Would you like to say something about your experience of interdisciplinary research? And also, I know that you are also interested in a lot of things, a lot of other subjects. Could you also tell us some example of interdisciplinary advancement of mathematics and other areas?
I actually changed my research interest quite a number of times. Most of the time is by necessity. There are always hot topics at any given time, and people will start working on the hot topics. But then all the low-lying fruits were picked already. And then after a while, things get too complicated to handle, or too difficult, or too specialized to handle. And then some other hot topic would come along, and then people would go into it. And in my experience, that's just my personal experience, I changed fields from such necessity. And also from talking to people. I discovered that when you talk to people, you learn much faster than reading. Even though nowadays on the internet, you can get all information you want. But still, when people write their things, they write it in such a way that is rigorous, that is detailed, but also difficult to read. When you actually talk to people, especially when the person is not prepared, then the person can only respond in a way that the person knows well, and mainly only the key points. So from my experience, just by talking to people, you get a lot of motivations to get into other fields. And of course, other people's viewpoints would help you suddenly realize that the viewpoints are usable in the problems at hand. So things actually evolve naturally. There's no deliberate effort to get cross-filterization or something. When it comes to other fields, I actually am not personally involved, but in my surrounding, like at Harvard, for example, there are centers or there are programs that try to be an interface for mathematics and other fields. For example, in economics, we have this Eric Maskin. Eric Maskin got a Nobel Prize at some point. I think it was 2007. And he's professor of economics and mathematics. And then there's Martin Novak, who was appointed professor of mathematics and biology and director of a program for evolutionary dynamics, which was funded by Jeffrey Epstein Foundation. And also there's a Center of Mathematical Science and Applications, which Xingtong Yao got the funding for from somebody in China. So you have such institutions or centers for interaction when the programs for different fields would be invited to sort of interact. But personally, I'm actually not working with anybody in other fields. The more traditional interaction would be about physics, but increasingly biology and chemistry and other fields come into the picture. I noticed that there are survey articles in the AMS written by, for example, Avner Friedman about biology, and then somebody about chemistry, alerting people to various possibilities. From the past, of course, we have seen a lot of success, like tomography, for example, in radon transform and that kind of thing. I think I spoke too much, so I should stop.
Okay, thank you very much. Professor Wustos, I know that ETH has a long, successful tradition in mathematical physics. For example, Einstein was a student there, and Hermann Weyl was teaching there also. So are there any other example of interdisciplinary fertilization right now in your department?
Oh yes. So mathematics is very close to computer science, and in computer science there is the part which is more theoretic, and so we have quite some strong contact with Emma Welzel, for instance, who got an offer by the computer science department many years ago, and so we tried to build a bridge between mathematics and computer science by making him an associate member of the department, and so there is a close connection with a theoretical computer science and mathematics. It is a pity, I must say, that this close connection somehow got more and more involved in teaching logic, and so this seems to be taken away from mathematics, where we had strong logicians, but that's how things go. Also, there are some connections between finance and the finance department and other areas of science at ETH. We have strong contact with a university. So there is research groups relating university and ETH. So we always, I always saw it as very important that universities at one place should collaborate. So they should enforce the collaboration, and I learned this from Berlin, where I did evaluated the 3 universities, and I saw that there are at places there are fields which did not interact, and so one of the strong suggestions was to interact and not to duplicate fields. So, for instance, logic, rather than to concentrate this at one place and getting there very strong groups. So the collaboration between fields and also within mathematics depend on the people being ready to discuss problems and to discuss questions, and to also be prepared to hear things which they don't know very well, but be patient to continue. And so this is a very important aspect. Another important aspect is educating graduate students and graduate students in a broad way, and not let them specialize too much. So this is what I can say about this point.
Oh, okay, thank you very much. So, and yeah, okay.
Yeah, maybe since specifically you were asking about the X-Chandelwald conjecture for the Shimura varieties, I think sometimes the interfaces between the different subject areas, in this case geometry and number theory, exists in some sense naturally, but it is also up to people knowledgeable in the areas to try to build bridges in the areas. In this particular case, the formulation of the X-Chandelwald in terms of unlikely intersection. So and also the Zanier and then Piller-Zanier's strategy to make use of geometric or to reduce problems about special points and so on into the questions having a geometric component, were bridges that were built towards solving problems in functional transcendent theory with input from geometry. So I owe it very much to people who have been able, the knowledgeable people who have been able to translate certain questions into different areas of mathematics.
Okay, so I have a follow-up question. So as the founding director of the Institute of Mathematical Research at HKU, so Professor MOK, in addition to what you just say, can you say also some other examples of facilitating course factorization of mathematics, for example, with other areas?
Yeah, so for instance, we had this Lie group program. So Borel, Professor Achmon Borel, was running this program on Lie groups for 4 months each year, from 1999 to 2001. So these were one of the inaugurating activities of the Institute. And there we brought in people from different areas, the basics in Lie theory, also in number theory, in mathematical physics, and in geometry. And they freely interact with each other. I think people actually learn a lot from that program. And some of the students actually got a lot of mileage from this this basic program, and recently some of them actually did excellent work after so many years.
Yeah. So I recall another example is we also invite people from medical school to give some.
Yeah. So if talking about interdisciplinary, talking about interdisciplinary collaboration, so again, you need some bridges. And in the event, so we had someone working in genomics, someone who was actually educated in mathematics and physics, and then we decided to run a seminar. This seminar on how life begins, how is life defined. So some very basic fundamental questions, and treating it like mathematicians are trying to axiomatize life in some sense. And of course, it was very interesting. Most of the lectures were delivered by people in microbiology or in genomics, but then we, on the one side, try to provide mathematical tools and also put in our perspective as a mathematician from the how to treat things rigorously and so on. So I think this is a kind of free exchange, which is intellectual exchanges that could be very useful for interdisciplinary research.
Okay. So thank you very much, Professor MOK. I think because of the limitation of time, so we would like to end this roundtable discussion. Okay, and let's thank our guest speaker and also Professor Fu for joining this roundtable discussion. Okay.
Okay, so thank you, Professor Ng, and all the other panel members. The joint academic conference has come to an end. Thank you all for joining us, and have a good day, and please stay safe.